right, now we're looking at applying our knowledge of trig graphs to real life situations. So we're going to start with a rabbit population in South Australia. And we're measuring time in months, and we can see that the input of our sine function here is in degrees. So we're going to take t in months but multiply it by 30 degrees to turn it into a degree measure for our sine. And then what we're going to get out is the rabbit population as a function of time. So what is the largest rabbit population predicted by this model? So what I'm really looking for here when it says largest, what I'm looking for here is the max value. We know that the maximum value of sine is 1. So my maximum value, so I'm going to call this R max, is going to be 12 plus 3 times 1. Now we don't know when this is happening. We would need to figure out what our t is to know when the max is happening, but the max of sine is always 1. So the max of this function then is going to be 15, and we're measuring in thousands, so 15,000 is the max population. How long is it between the times? So now what I'm asking with how long between times when it reaches consecutive peaks. So that's asking how long is it between maxes, consecutive peaks, those are the maxes. So how long between, what I'm really asking for is period. So I know my normal period in degrees is 360, so my new period is going to be 360 divided by my b value, which is 30. So 360 divided by 30, that's going to give me 12. And so how long is it between peaks? I know that I'm measuring in terms of time, so this is 12 months. So what we're looking at here is the cycle is happening over a year. All right, so now let's sketch it over the year. And we're actually sketching over 2 years, so we're going to see 2 full cycles. We know that our midline value is going to be 12, our principal axis, and we've already said the max is 15, so let's see how many lines we have here. 9, 10, 11, 12, 13, 14. I'm going to pretend like we've got 15, so I'm going to put in a max line of 15, and then actually, I'm not going to put it way up here. Let's count by, let's say we're counting by 1.5. So then this would be 3, 6, 9, 12 here, and then 15 here. So I do want to make my graph look nice. I don't want to add in lines if I don't have to. So my max is going to be 15. My min is going to be 12 minus 3, so center line minus the amplitude. So 12 minus 3 is going to put me down here at 9. And here's my principal axis at 12. So I know that I've got a sine function, have no negative, so I'll start in the middle, and I want to complete 2 full cycles. So about halfway is where I want to complete 1 cycle. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So if I go over 7, and actually let's make this an even number. So instead of going over 14, I'll go over 12. 1, 2, 3, 4, 5, 6 will put me back at the middle, which means at 3 I'll be to my min. And here's 1 full cycle, that must be 12 months. And then I'll repeat. Max, back to center, min, back to center. Okay. So similarly max, and now I can make my smooth curve of my rabbit population, trying to hit my points as best I can. All right, so there's over 2 cycles. That's what it asked me for, 0 to 24 months. All right, so this is T measured in months, and this is population measured in thousands, and specifically thousands of rabbits. Find the longest time span for which the population is greater than 13,500. So now I'm looking at my graph. I've actually put in the line inadvertently for 13.5. So the longest time span is going to be the time between my points of intersection. So somewhere around here, that's what I'm looking for. And of course that's going to be equal. My graph is symmetric. So I'm looking for this. I'm going to use my calculator to find that time span. So in my calculator, I'm going to make sure I'm in degree mode. And I'm going to come in and graph both of these lines. So 12 plus 3 sine 30x. And I'm going to graph the line 13.5. I'm going to make my window match. So let's go from 0 to 18 and count by 1.5s. And then on my y-axis, I'm going from 0 to 24, and I could count by 2s. All right, so here's my curve. And then I have my line 13.5. So I'm looking for these points of intersection. So calc, intersect, line 1, line 2, and based on my graph, my first point of intersection looks like it happens somewhere around month 1. So I'm going to type in 1 as my guess. Oh, and it is exactly 1. That's nice. And now I'll calc my second value, my intersect. Since I know that this was exactly 1, my guess for my second one is going to be 5. And sure enough, I get 5. What this tells me is that actually I could have solved this algebraically as 1. Or sorry, I could have solved this algebraically as well. So this point of intersection happened exactly at 1 and exactly at 5. So the longest time span, 5 minus 1, is 4 months. So let's look and see here. 1, 2, 3, 4 months is the longest time span. So give a possible explanation for the behavior of this model. Why is it that rabbit populations increase and then decrease? Well, if we think about rabbit populations, rabbits are definitely one animal that breeds very quickly, but an environment can only support so many rabbits. So at some point you reach the maximum amount of rabbits that an environment can support. And at that point, either due to predators or lack of food, the population will decrease until it hits a point where the environment can start supporting more again. And so the population of rabbits is always going to cycle.